Alright, so this video is about the different number bases. So let's get started. So in this video we're going to introduce some of the different basic number bases, and then we're also going to talk about how to convert between them. So first is decimal numbers, and decimal numbers are base 10, meaning they use digits 0 through 9. And these are probably what you're most familiar with. And if you're looking at the examples, the smaller 10 to the side represents the base, so that it's base 10, and you'll see that with these other numbers too, and that'll be important to know when we're converting between them. So now we have binary numbers, which are base 2, meaning they use digits 0 and 1. And computers use binary because the two states, which represent off and on, basically, are easier to process and less storage intensive than if a higher number base was used. So that's a fun fact about binary. And binary can also be unsigned or signed, which we'll talk about in a second, but that'll be irrelevant when we're converting to decimals. So yeah, so we see the examples. It only uses the ones and zeros, and the 2 to the side indicates that it's binary. So now we have octal numbers, which are base 8, meaning that they use digits 0 through 7, so 8 values in total. So lastly, we have hexadecimal numbers, which are base 16, meaning that they use digits 0 through 9, and they use characters A through F to represent 10 through 15. Because if you try to use 10 through 15, it'd be unsure whether, if you had like a 15, whether that's actually 15 or 1, 5. And hexadecimal numbers are useful for representing things like memory addresses, since it can represent very large numbers in way fewer digits. And here's some examples down here. And you'll see that they use the characters in there, and that you see the base 16 to the side. Okay, so now that we know our number bases, we can start to talk about how converting between them. So first we'll talk about converting some of our number bases to decimal. So for our purposes, we'll just call each digit in the number a bit. The leftmost digit we'll call the most significant bit, and the rightmost will be the least significant bit. So to convert to decimal, we're going to follow this basic notation here. Basically, you're going to multiply each digit by the base, and then that base is raised to a certain exponent. The least significant bit will be multiplied by a base to the 0th power, and as it goes to the left, it'll go up 1 by each term. So we have an example here of converting an unsigned binary number to decimal. So we take each bit, multiply it by the base, raise the exponent, and we simplify that, and so the number 1101 binary is 13 decimal when we convert it like this. So yeah, that previous example, it specified that the number was unsigned, but what does that actually mean? So an unsigned binary number, it will always represent a non-negative decimal value. So for example, a 4-bit unsigned binary number can represent decimal values 0 through 15. But then on the other hand, when you do have a signed binary number, that means that it could represent a negative decimal value if the most significant bit is 1. That's the digit to the leftmost digit, as a reminder. Otherwise, if it's not, then the decimal value will simply be the same as the unsigned counterpart. And there's actually multiple methods used with signed binary numbers that will give different representations for the same number. But for this purpose, we'll be using the signed 2's complement method, because it avoids the issue of counting 0 twice, unlike some of the other methods. So with that in mind, a 4-bit signed binary number can represent decimal values -8 through 7. So basically half the values will be unchanged, and the upper half will represent negative values instead of that upper half of the positives. So yeah, now we're going to convert the 1101 binary number to decimal again, but this time we're going to assume that it's signed. So the calculation, you see, is that most significant bit is going to be negative, and that's going to lead to it now being -3 in decimal instead of 13. Alright, so now we can talk about switching between binary to octal and hexadecimal, and vice versa. So 3-bit binary numbers in an octal digit can both represent decimal values 0 through 7. So you're able to switch between them willy-nilly. And the same thing with hexadecimal digits, except it's with the 4-bit binary numbers. So we have some examples here. But this first converting this binary number to an octal. So first, to make it a little easier to see, we separate out into groups of 3. And when you don't have exactly 3 things in your leftmost group, you just put zeros in front of it until you do have 3 terms or 3 digits in the term, and then you will simply take each one of those groups and convert that binary to the appropriate decimal value, and that decimal value will it'll never be 8 or 9 because it's octal, but it'll be any of the others. It could be any of the others. So yeah, we take that same number, that same binary number now, and we convert it to hexadecimal, which is splitting it into groups of 4 digits, and we'll be converting each of those groups into a single hexadecimal digit. So the 8-digit binary number becomes a 2-digit hexadecimal number, which kind of goes to show our point of how hexadecimal numbers can represent very large numbers in a much shorter space. And then we got the inverse, where you just take each digit of an octal and you'll convert it to each digit to the 3-bit binary number, and then the same thing with the hexadecimal, except with 4-digit binary numbers for each digit. So that brings us on to converting from decimal. So you can convert decimal values into other bases by simply repeatedly dividing them by the number base you are wanting to turn them into. So yeah, each time you do that, then the remainder will be taken out. And once taking out the remainder leaves your quotient as 0, then putting the remainders in reverse order will actually give you the newly converted number. So yeah, as an example, we'll convert the decimal value 92 to octal. So we're going to have 3 columns here: the quotient, what we're dividing it by, and then the remainder when we divide it by this number. So dividing 92 by 8, it's going to go into it 11 times, but there's going to be a remainder of 4, so we take that out. So yeah, our quotient now is 11, divided by 8 again. We have a remainder of 3, and then 8 goes into 11 one time, so our quotient is 1, divide by 8 again, and our remainder will be 1, and that's going to leave our quotient at 0, so we're done now. And to get our octal number, we're going to start from the bottom remainder and put that and go up, and that's simply going to give us our new converted number. So stringing our remainders bottom up will give us our new number, which in this case is 134, and that's going to be our newly converted octal number. So that brings us on to our practice. So we have these 3 problems here. First one, converting a binary number to decimal, and we'll consider both the unsigned and signed cases. Number 2 is converting a octal number to hexadecimal. And then our last one is converting a decimal number to binary. So I'm going to show start showing the solutions here in a second. So if you want to try these on your own, now is the time to do them. Otherwise, we're going to start looking at them. So for this first one, we're going to look at the unsigned case first. So we take each digit of the binary number that equals 1, and this is a simplified version of what we showed earlier. So yeah, we're not considering the zeros at all. So yeah, just taking the digits that have 1 on them and taking note of which bit that is, bit number that is, and that's being raised to that power. So add all these together, and we'll get 83 as our unsigned decimal value. And now doing the same thing for the signed, the most significant bit is 1, so we know it's going to be negative. So that first term in adding this up is going to be negative, and consequently we have the result of negative 45 as our decimal value with the signed case. For number 2, we're converting 651 to the octal base to hexadecimal. So first we're actually going to convert it to binary by taking each digit of the octal number and converting it to the corresponding 3-bit binary number. And then from there, we're going to reorganize it into groups of 4, remembering to put the zeros at the beginning of the most significant here so that it's a group of 4. And then from there, it's pretty easy to be able to convert those groups into the corresponding hexadecimal digit, which would be, and then in total we have 1A9 as our final hexadecimal value. And then lastly, converting 71 decimal to binary. We're going to do this table again. So yeah, take 71 divided by 2. That's going to have a remainder of 1. And then 35 divided by 2 again, remainder of 1 again. 17 again, remainder of 1. And we have 8, no 0 remainder. 4, 0, 2, 0, and then 1. And the remainder is 1, and that's going to mean our quotient 0, so we're done. So we go bottom up with our remainders, and that's going to give us 1, 0, 0, 0, 1, 1, 1 as our new binary value. So yeah, hopefully that all made sense. If you have any questions or feedback, feel free to leave them in the comments. I'll see you guys later.